Welcome, everyone. Thank you for joining us today. My name is Natalia Martin, and I'll be a moderator for this webinar. Today is an official launch of Andrew Ginter's new book, Engineering Grade OT Security. Once again, Andrew, congratulations.
Thank you.
In case some of you don't know, Andrew is a VP of Industrial Security here at Waterfall, and this is the launch of his third book. A couple of notes before we start. This webinar is being recorded. An email with the link to the recording will be sent out to all of you within the coming days. There will be a Q&A session at the end of the webinar. Please make sure to submit your questions into a Q&A panel at the bottom of your screen at any time during the session. We will try to answer all questions at the end of the webinar. But in case we're out of time, which happens sometime, we'll make sure to follow up with you individually via email. And with that, Andrew, the stage is yours.
Thank you so much, Natalia. Hello, everyone, and welcome welcome to the webinar. Thank you for joining us. Let me move this forward. Here we go. This is my third book. I'm going to go through the the table of contents. That's pretty much my my agenda for this webinar, just to give you folks a summary of what's in the book for those of you who aren't actually going to read it. But let me start with with the prologue. This is my third book. I put a few pages in there, sort of reflecting on the process of writing three books. My first one, SCADA security, what's broken, how to fix it. Met with mixed reviews. Okay, the feedback I got ranged from, Andrew, I disagree so fundamentally with your premise that I could not finish reading the book, all the way over to, Andrew, it must have taken weeks of your life to write this thing, yet everything you document is obvious. What would possess you to spend so much effort documenting the self-evident? So from disagree fundamentally to so obviously true it's not worth writing down, and everything in between. I learned two things from that. Two big things. One is nobody likes a critic. I criticized a widely used approach for cybersecurity. The title says it all: SCADA security, what's broken. In hindsight, it's much easier to criticize an existing approach than it is to propose a new one, so other people can criticize your approach. So my apologies to everybody that I offended in the first book. Second thing I learned is experts disagree. There is no consensus in this industry. In the second book, Secure Operations Technology, I took a deliberately different approach. Instead of criticizing, I swung the pendulum to the other extreme. I said, let's document what the world's most secure sites do differently. First they do this, then they do that, then they do the next thing. If you see value in any of these, you pick and choose. And I had people, the main feedback I had from that book was, Andrew, this is all good stuff, but when should I use each of these techniques? Where should I use each of these techniques? Where do I not need to use these techniques? Where, what kinds of, most importantly, where do I use it? When do I use it? And why? Can you explain why I should use these things here, but not there? And so in my third effort, I swung the pendulum back to the middle. I'm not criticizing anybody. I'm not documenting. You pick and choose. I am, in the third book, trying to prescribe, saying, look, here's what we've got. You should do this here for this reason, and that there for that reason. So I'm trying, the voice I've taken is prescriptive. And, where to begin? Let me interject. The voice I've taken is prescriptive. This is my third effort. Bluntly, I see retirement staring me in the face within the next 5-ish years, give or take a few years. Depends how long this body holds out. And so, what I very much hope, these books have been sort of an opportunity to take a lifetime of, what wisdom I have and try and express it for another generation. What I hope is that you find my prescription, my perspective on what you should do, when you should do it, why you should do it, why we should all do it. I hope you find my advice useful. I hope you find it convincing, and if not convincing, then at least find it useful, I hope. Do send me feedback. If I write another book, I learned from the feedback on the first three. I rely on feedback from practitioners and experts like yourselves. My contact information will be on the last slide. This book, has 10 chapters and a couple of appendices. The subtitle of the book is A Manager's Guide. I Fly High and Slow. So hopefully it's accessible to everyone who wants an introduction to the field. In Appendix B, the very last part of the book is actually about 25% of the book. I take the contents of the previous book, Secure Operations Technology. What do the world's most secure sites do differently? First they do this, then they do that, etc. I take that book. It's a much more technical approach, much more detailed approach than the high and slow approach I'm taking in this one. I reproduce the most important 4 chapters out of the black book into the gold book, so that you don't have to buy the black book if you want the methodology, the secure operations technology methodology that I observed the world's most secure industrial sites using. It's all there in the appendix of the black book, but it's a change of, speed. For the first 3 quarters, I fly high and slow. And then for the appendix, it's a much more technical book. I dive low and fast. So, my apologies. But hopefully, by the time most readers hit that low and fast appendix, if you folks read it at all, you'll have enough introductory material in the first 3 quarters of the book to actually make sense of at least some of the appendix. So much of the material is introductory. Chapters 1 and 2, I'm just going to skip here. I'm not going to introduce what is OT, what is an industrial control system. If there are listeners on the webinar who need that background, my apologies. Have a look at it. I'm going to start really quickly with attacks. And this is something that is not news to anybody who's been following the Waterfall webinar series. Reese McNamee has been talking about this. He's the principal researcher for the Waterfall Threat Report. I've been talking about these findings on a couple of different webinars. The bottom line is that where attacks with physical consequences in manufacturing and heavy industry, where attacks with physical consequences were a mostly theoretical problem in the previous decade, the 20-teens, they've turned into a real problem going forward. They've turned into an exponential growth this decade. Now, we only have a few data points, 3 of them. The last one here is a projection. But it looks like the world has changed. And, it gets worse. Most of this is ransomware. Some of the ransomware groups are backed by nation states with effectively unlimited resources. So some of the ransomware coming after us is actually nation state grade attacks. Other ransomware groups are so wealthy that this has been so profitable for them that they can afford to purchase, they buy or pay someone to build nation state grade attack tools. And so what we've concluded in the threat report is that the pervasive threat is ransomware groups using nation state grade attack tools. They seem to be running a couple of years behind the bleeding edge of nation state tools and techniques, but only a couple of years. And so the bad news is what we see the nation states doing to each other today, we should expect ransomware to be doing to everyone with money in a very small number of years. And here's the problem. If this exponential growth continues, and we don't know if it will, but if it continues at this rate, it's basically increasing tenfold every 2.5 years. By the end of 2027, we're going to see between 4,000 and 5,000 attacks, taking down between 15 and 20,000 industrial sites. This is a crisis coming down the tracks at us. And, in my best opinion, in my best estimation, all of these industries, we, the defenders, are not going to be able to build a cybersecurity wall big enough and strong enough and fast enough to stop that train. The good news is that there's a way to step off the tracks. And that's what I deal with in chapter 4. And again, you've heard this before if you've heard any of my recent webinars. This is about the Department of Energy in the United States has funded Idaho National Labs, basically paid for a bunch of PhDs to develop a strategy for cyber-informed engineering. And it's not just a strategy, the first deliverable of that effort, the cyber-informed engineering implementation guide is out. In my opinion, the implementation guide is misnamed. It's less a recipe for how to do cyber-informed engineering, and it's more a checklist of questions. Have you thought about this? Have you asked this question? You should ask that question. It doesn't really say what to do with the answers. Now, some of what you do with the answers is obvious from the question, but other times it isn't. So, but it's a step, it's a concrete deliverable, and I recommend it to everyone in the space. But what is cyber-informed engineering? It is, I call it, security engineering for short. It is, it's informally, it's described as a coin with two sides. One side of the coin is teach engineering teams about cybersecurity. Been singing this song for 20 years. There's nothing new in that song. The other side of the coin is use powerful engineering techniques to address cyber risk. What does that mean? Well, the engineering profession has been addressing physical risk, has been addressing threats to public safety since the beginning. I mean, what was the first engineer? The first engineer was the person running the engine on a train. What was the number one priority for the first generation of engineers? It was don't collide the trains, because there's a limited amount of track. And if you've got two trains in two different directions sharing the track, you've got the potential for a disaster. So since the very beginning, it's been all about safety. For passenger trains, it's all about public safety. And so the engineering community over the course of a century has developed some very powerful techniques for managing physical risk. A classic example is a spring-loaded valve. If you are a technician in a coal-fired power plant, you're managing 6 massive boilers. Each of these is 4 stories tall, massive devices. You calibrate the instrumentation. You have the gamma ray testers to test the corrosion on these devices. And if one of these boilers blows up in your face because it overpressurizes, you're dead. You spend all day, 8 hours a day, every day. You're the technician responsible for these boilers. You spend 8 hours a day inside of the kill zone of a worst case boiler explosion, blast radius. How would you like to be protected from a cyber attack that overheats the furnace on one of your boilers? Would you prefer a mechanical valve where there's a hole in the tank? If the steam pressure becomes too high, it forces a piece of steel against a pin that breaks or a spring that deforms. The steam escapes and there's no explosion. Would you prefer a mechanical mitigation for that cyber risk? Or would you like a longer password on the PLC controlling the furnace? The best answer I've heard to that question is, Andrew, you've asked me the wrong question. I want the mechanical valve, or 3 of them, because it's mechanical. These things do wear out. I want the password on the PLC, and I want a boatload of cybersecurity beside that. It's my life on the line. Thank you. I want protection. And this is the right answer. When human life is at risk, there's a clear expectation that these workers are going to be really thoroughly protected, even from the worst kind of nation state ransomware or whoever else comes into our systems. Another couple of lessons, I talk about engineering grade solutions. The overpressure valve is engineering grade. It is deterministic. It always does the same thing. The failure modes can be modeled mathematically. It's called the bathtub curve. New devices tend to fail more often than average because of manufacturing defects. And then the failure mode sort of settles out at a very low random level and then starts picking up as the devices get very old because the metal ages, you have fatigue and so on. You have corrosion sometimes. And so, deterministic, mathematically modelable. What's the opposite of engineering grade? Imagine that we have a bridge that, there's a new design for bridges, 1/3 the cost of existing suspension bridges, but the design is riddled with harmonic frequencies. What does that mean? The smallest vibration tends to build up over time to tear the bridge to pieces. People, a large group of people walking over the bridge will trigger a harmonic vibration. And so what we do is we, brain blank. What we do is, sorry, I got people texting me here. I'm distracted. Harmonic frequencies. Back to the message here. The designers of the bridge have built active vibration dampers into the bridge. Hydraulic dampers, quadruply redundant power supplies, artificial intelligence controlling the dampers. The bridge feels rock solid because of these dampers dampening out the harmonic frequencies. How happy would we be driving across the bridge every day if we knew that the design engineer hoped that if there was a cyber attack on the AI, we could detect the attack in time to prevent disaster? How happy would we be, knowing the design engineer hoped that if we detected the attack, we could scramble an incident response team fast enough to defeat the attack before the AI is compromised and the bridge disintegrates? Hope is not what we expect of design engineers. We expect a bridge to hold a specified load in a specified operating environment for a specified number of decades with a high degree of confidence, with a large margin for error. I was talking to a civil engineer who designs footbridges for people, like coming out of stadiums into parking lots over roads. I asked, how do you know the load? And he says, it's a footbridge. There's barriers on the other side. You can't drive vehicles across it. But, worst case load is wall to wall water, 2 meters of water. The average person is less than 2 meters tall. The average person is 90% water. And so you model the weight of water, wall to wall, end to end. That's your maximum load, he said. You design the bridge for 10 times that load. You take that maximum load and you multiply it by 10, because these are people. Failure of the bridge under load is unacceptable. So that's the concept of engineering grade. The community has been doing this for 50 years. A lot of these techniques just need to be gathered into a body of knowledge. We've been using mechanical valves and other design techniques on the engineering side for decades to address the risk of earthquakes, of hurricanes, of tornadoes, of fires. We need to start applying these powerful tools that are unique to the OT space, that don't exist in the IT space. I mean, where's the mechanical valve in the NIST cybersecurity framework? It's not there. It's not a cybersecurity tool, but it's an engineering tool that can be used to address cyber risk. This is what Security PHA, a book from 2019, I very much recommend it. Came out of the ISA, written by the folks at Connex. It's brilliantly written. I had no idea how to do this when I read the book, and afterwards I said, well, this is obvious. It's obviously the right way to do this. It's brilliantly written. I recommend my own book, but you don't have to buy it, again, because the new book has the important parts of the methodology in the appendix. And this is a book on, let's call it information engineering. All cyber sabotage attacks are information. The only way you can sabotage, the only way an industrial control system, a PLC, anything can change from a normal state to a sabotaged state is if attack information enters the system. And so if we can control the flow of attack information, we can control the attacks. And that's what the book talks about, is controlling the flow of information that might be entering our systems and putting those systems at risk. I've got a chapter 5 on network engineering. I talk about ways to control the flow of information, to control the flow of information across network boundaries. Where do you use network engineering? You use it at criticality boundaries. Okay, when you've got a network whose worst case consequence is things blow up and people die, connected to a network whose worst case consequence is we get sued, we get sued and we have to pay for emergency cleanup. When we have that connection between two networks with dramatically different worst case consequences of compromise. That's where we have to do network engineering, at that criticality boundary. And there's, I go through a lot of examples of network engineering. EPRI has a methodology out for the industrial internet, which is, brilliant in hindsight. Again, obvious in hindsight, but, to me, anything that's obvious in hindsight and, not obvious to begin with is brilliant. There's analog signaling using, 4 to 20 milliamp loops to send small amounts of information across criticality boundaries in a way that cannot communicate malware into the protected system, used primarily for safety systems. There's dependency analysis, which I'm going to talk about in a minute. There's data abstraction. These are all tools for controlling the flow of attack information. The most widely deployed solution in the network engineering space is the unidirectional gateway. And, for the record, this is what Waterfall does. Waterfall invented the unidirectional gateway, but it occupies, I think, 2 sections in chapter 5. The focus of the book is on answering the question, how much is enough? And this is a tool in the network engineering toolkit to be deployed at criticality boundaries. You don't deploy these network engineering tools. You do not deploy these tools inside an industrial network. Why? Well, if you compromise the PLC and it misoperates the furnace, the furnace overpressurizes. This is unacceptable. If you compromise the HMI and it tells the PLC to overheat the furnace and the furnace overheats and the boiler overpressurizes, this is also unacceptable. Typically, inside of an industrial network, everything is at the same level of criticality. The industrial network either has unacceptable consequences or acceptable consequences. And so what we see is firewalls deployed routinely inside the industrial network to prevent east-west spread of any malware that might get in there, to prevent north-south spread of malware. We see firewalls, of course, deployed throughout IT networks, and we see network engineering techniques deployed at the boundary between those two kinds of networks that have very different worst-case consequences of compromise, very different criticalities. Unidirectional gateways, if you've never heard of them, let me burden you with a 2-minute intro. The gateway is a device that sits at the boundary between these two networks with very different kinds of criticality. Under the hood, there is a circuit board on the left with a fiber optic transmitter, a laser in it. There's a circuit board on the right with a fiber optic receiver, a photocell, and there's a short piece of fiber on the front of the device. So what that means is we can send from the industrial network out to the business and nothing gets back, nothing at all. There is no laser on the receiving circuit board. It cannot send anything back into the industrial network. It's, with a firewall, if you configure the firewall correctly, it should not send anything back into the industrial network. This is engineering grade unidirectionality. It physically cannot send anything back. You can completely rely on this being one way. The software, in a sense, is where the magic is. The software makes copies of servers. If you have an OPC server or an Oracle server on the industrial network, that is the focus of your IT/OT integration efforts. That server contains all of the data that is allowed to be shared with the enterprise network, with business users, business systems. The gateway software logs into that data source, username and password, nothing tricky, asks the data source for everything that's changed since the last time we logged in, a second ago, usually. Gets back, 3, 4, 5 megabytes of data, pushes that data through the weird one-way hardware. And on the other side, the software logs into an identical server. If it's OPC on the inside, it's OPC on the outside. If it's Pi on the inside, it's Pi on the outside. If it's Oracle on the inside, it's Oracle on the outside. Logs in and inserts the data into the enterprise server. And now all of the data that's allowed to be shared with the enterprise is out on the enterprise network already. We're not forwarding messages. These are two different conversations. The gateway is typically a client on both networks. It's a client of the industrial server asking it for data. So that conversation is small question, give me new stuff. Big answer. Here's your new stuff. And on this side, on the outside, on the enterprise network, the conversation is a different conversation. Big command, insert all of this data. Small answer. Yep, that worked. Now what? It's a client on both sides, not a router like a firewall. That's sort of the key concept. But the point is, one way out, nothing back. You always need to send something back. So this is the 99% case. And, I talk about the 1% case in chapter 5 as well, in terms of other kinds of network engineering, other kinds of ways to move information around when you have to move information back into your industrial network and potentially put that network at risk. I wanted to say a few words about dependencies. In previous efforts at describing network engineering, I find myself never getting to this topic. So let me stick it in the middle of the webinar here. Dependencies are important, a great many, and I don't have the numbers. I've asked the research team for the next version of the threat report to gather these numbers, but I have the sense that a great many, a large fraction of the ransomware attacks that took down physical operations last year did it through dependencies. The ransomware hit the IT network, crippled the IT network, and operations stopped. Why? Because operations depended on functions that something on the IT network was providing, and the IT network was crippled by the ransomware. Classic example is Maersk Shipping. NotPetya took down the IT network at Maersk in 2017. The worm never got into the OT networks. Maersk is the world's largest container shipping company. It never got into the OT networks in the ships. It never caused the ships to run aground. None of that happened. Okay, the ships still came into port like they always did. The NotPetya did not get into the cranes in the port. The cranes were still operating safely. They could take the containers off the ships in port and put them on the trucks. What was crippled was the container tracking system, this thing that kept track of EDI files that told the truck driver where to take each of these containers. Because these EDI, that container tracking system was crippled, nobody could tell the trucks where to take the containers, and so everything stopped. Shipping, container shipping more or less stopped at Maersk. Give or take a little bit of manual intervention, but it was reduced dramatically to a very small fraction of normal shipping because the IT network was crippled. And so if you look at that, what we have is not two networks, a safety critical network on the ship or on the crane, and a business critical network on the enterprise side. What we have is in fact three networks. One of them is safety critical, don't run the ships aground. The other one is a business network. This is where you conduct business, this is where you bill people. And the third one is reliability critical. This is where the container tracking system is. It's essential to the reliability of the industrial system, the reliable operation of the physical part of the business. There's nothing you can do to the container tracking system that can cause an unsafe condition. This is not a safety critical network, but it is a reliability critical network. And so how do we protect this? Well, to me, the right way to protect it is to put network engineering in place, unidirectional gateway on the ships, on the cranes. You can monitor the equipment, but nothing gets back into the safety critical system to put that system at risk. But some of the network engineering techniques, not all of them, some of them need to be applied to the reliability critical network as well. In particular, you have to do the dependency analysis. If we've got a safety critical network that has to continue unimpeded, it cannot depend on functions on the business network. Similarly, if physical operations are to continue unimpeded, what happens the next time one of these reliability critical systems goes down? Well, we should train our incident response people to make a beeline for that system, have it hosted on, let's say, a virtual machine, restore the last known good version of the virtual machine, replay the transaction log, the right one's transaction log, so that the tracking system is right up to date, and bring it back online so that a couple hours after the incident, we're moving containers again, or moving gasoline in the pipeline, or, we've got the physical process working again. That's only possible if we've done the dependency analysis, not just on the safety system, but on the reliability critical system as well. If we cannot have the reliability critical system depend upon functions in the enterprise network that are still crippled, because we haven't restored the whole enterprise network first. So this is sort of a non-trivial example of network engineering, where you've got to understand your consequences really thoroughly, and take measures to protect each of these kinds of networks in a way that's appropriate for that kind of network. I've got a chapter on risk. I point out that, look, if you've got high frequency, low impact incidents, I mean, in a large organization, pick an organization with, I don't know, 100,000 employees worldwide, you're probably going to have, a couple of dozen, let's say 20 malware incidents in the year. What happens? Well, malware gets in, and you detect it, and you have to isolate the machine, or 3 of them, erase them, restore from backup. Each of these incidents is an emergency. You've got an incident response team that's tracking this, that's doing this. Each of these costs you, let's say, $100,000. You've got 20 of them in the year. It's going to cost you $2 million a year on average for these high frequency, low impact incidents. And so, the right model for that kind of incident is risk equals consequence times likelihood. Not even likelihood, it's consequence times frequency for these high. That doesn't work for low frequency, high impact events. Take an extreme example. How many times has the entire North American power grid been knocked out by a cyber attack? Well, it's never happened. Well, could it happen? Yes, it could. Nothing is ever completely secure. Given enough time, money, and talent, one can imagine a cyber attack that would take down, the entire grid, or a large fraction of the grid. So what likelihood should we assign to that? Well, any number we put in there, any probability we put in there, is going to be made up, because we don't know how likely an attack like that is. People use qualitative likelihood. They say, well, let's do a score from 1 to 5, or from 1 to 3. 1 is really unlikely. And, you do this grid. This is a really unsatisfying way to model risk for high impact attacks, because cyber attacks are more deterministic than random. Imagine that a small factory gets hit by, I don't know, the snake ransomware that has code in it to take down industrial systems. Has to be cleaned out. They're down for 10 days. They come back. Imagine, however unlikely this seems, imagine that the factory learns absolutely nothing from the incident, and comes back and changes absolutely nothing, and exactly the same ransomware hits them a month later. What's almost certainly going to be the outcome? It's almost certainly going to fail. It's going to hit that factory and take it down in exactly the same way. Deliberate attacks are not so much random, they are deterministic. If the same attack hits you twice and you've changed nothing and you went down the first time, you're going to go down the second time, almost certainly. These are deterministic, not random. Probability is the wrong way to model them. A better way to model them is design basis threat, which is a function of risk that says, look, risk is a function of consequence, and it's a function, it's not a product. It's a function of consequence, intent, opportunity, and capability. Basically, the function is something like the sum of all consequence. If your adversary intends to take you down, and the capability of the adversary is greater than the capability needed to take you down, then you will suffer the consequence. You will go down. This is a better model. And so the right way to model risk is to ask, how capable are my adversaries? Or how capable an adversary am I going to defend against? How capable an adversary am I going to require my security teams to defeat reliably? And, what kinds of attacks am I going to say, if one of them hits me, I'm going to go down? That's drawing a line. In physical security, it's called a design basis threat line. I'm proposing we adopt that terminology, call it a cyber design basis threat. And you might ask, yeah, but we're talking risk now, not cybersecurity. Insurance is a tool to handle risk. Can't we just buy insurance? And the answer is sometimes we can, sometimes we can't. When NotPetya hit, the insurance industry changed. The regulator for the Lloyd's syndicate in London, which is a lot of insurance companies, but not all of the world's insurance companies. Lloyd's is the leader in the insurance industry. The regulator for Lloyd's said the $1.4 billion loss that Zurich had to reimburse Merck Pharmaceutical for was unacceptable. And they changed the law. Nobody in the Lloyd's syndicate is allowed to issue silent cyber coverage anymore. If you have a $2 billion general damages policy, it has a clause in there saying cyber is excluded. If you want cyber coverage, you have to buy a separate cyber policy. And those policies are capped at about 200 million pounds. You used to be able to buy a $3 billion cyber policy. You can't anymore. It's illegal in the jurisdiction of the Lloyd's syndicate. You're capped at 200 million. Lloyd's has said it's just too dangerous. We cannot offer more coverage than that. The industry is gonna go down. So coverage for small amounts is available. Coverage for large amounts is not. The largest businesses, British Petroleum, when Deepwater Horizon happened, suffered a $69 billion loss. Now, Deepwater Horizon was not a cyber attack. Do not misquote me. It was a physical failure. But it's an example of a huge loss. British Petroleum was rich enough. They absorbed that loss in one quarter and kept going. You might argue for British Petroleum, that was an acceptable loss. But, here's the thing. If insurance companies refuse to cover you for more than 200 million, is it reasonable? Is it reasonable to self-insure for very large losses? Even if you can afford it, you're going to suffer. The British Petroleum executives suffered criminal charges. There was loss of life, I believe, if I remember correctly, in the incident. There were shareholder lawsuits saying, look, this should never have happened. So, what is reasonable? The insurance industry is saying, no loss over about $200 million is reasonable. We're not going to cover you for it. Which brings us to chapter 7. Having talked about risk, let's pull it all together. Let's answer the question, how much is enough? And what I recommend is that for network-based attacks, the pervasive threat is nation state. We have to protect against nation-state grade attacks coming across the network. Now, you might ask, well, some of the ransomware is nation-state grade. Some of it has been affecting OT, but the numbers are still small. Can we just sit on this for a couple of years and see how it develops? I suggest that the answer is no. Imagine that you are the chief security officer at a large manufacturer. One of these nation-state ransomware types hits you and you suffer a $500 million loss or $1 billion loss. Emergency, you get everything back running. And a week, 5 weeks, 8 weeks later, there's an investigation. It might be the government investigating you. It might be your board of directors investigating you. It might be your CEO pulls you into the office and says, okay, explain to me in one syllable words, what happened there? If you tell the truth, if you say, look, we knew that if one of these nasty ransomwares came after us, we'd go down. We just didn't think they'd hit us this year, so we didn't take any appropriate defenses. You're going to be fired. Okay, this is the wrong answer. We cannot count on the good intentions of criminals not targeting us this year. So I maintain that the pervasive threat across the network is nation state grade. And when we have unacceptable consequences in our OT network, the engineering profession has an obligation to deploy network engineering, to deploy strong deterministic protection at the boundary between the network with unacceptable consequences and the network with acceptable consequences. So some concrete examples, and I go through these in chapter 7. A small shoe factory. What's the engineering grade design in a small shoe factory? You've got, I don't know, 30 machines, 20 employees. Each of the machines has yellow tape around it. Okay, it says stay out of the machine. If one of these robots goes crazy and is obviously malfunctioning, and you and I are sipping coffee outside of the yellow line, what do? We look around and say, excuse me, someone should turn this off before it hurts itself, because we're safe. The robot can only reach to the yellow line. We're outside the yellow line. There are no safety threats. I mean, what's the biggest safety threat in here? The biggest safety threat to workers in an operation like that is when there's a malfunction, when there's a part worn out in the robot, and a technician has to reach into or crawl into the robot and find that part and replace it. If you crawl into a robot that turns on because of a cyber attack, when you're inside of it, you're in very deep trouble. So what does the technician do? They go to the power switch. They take the switch and physically turn it into the off position. They put a lock on that lever. They lock the lever in place. They put the key in their pocket, and now they crawl into the machine, because it's not physically possible to activate the power to the machine anymore. Forget cyber. It's not physically possible. So if you've taken physical measures to protect the safety of your workers in this system, what's the worst case? If ransomware or someone else comes in and makes a mess of your factory, well, you have to shut down. You have to bring in, gurus, cybersecurity gurus on an emergency basis. You have to pay through the nose to bring these gurus in to clean up the mess. And it takes them 10 days. For those 10 days, you lay off your 20 employees because they have nothing to do. They're mad at you. And then you're back up and running, and you bring your employees back, and you schedule overtime, because you got to make up lost production. You schedule overtime shifts. You have to pay your employees time and a half or double time. By the end of the quarter, the employees have more money in their pocket than they would have at the beginning of the quarter. More money than they thought. You've paid what? $3 million to clean the mess up on an emergency basis. You paid another $8 million in overtime. It's an $11 million hit. For a small company, that's a lot of money. But for an $11 million hit, you can buy insurance, have the insurance pay you back the $11 million, and you're good. This is an acceptable loss. What kind of cybersecurity is demanded here? Ask your insurance company. They're going to tell you what they regard as reasonable protection for that class of asset. Do what they tell you and a little bit more. Do not make the mistake. A lot of people make the mistake of trying to minimize the insurance policy costs instead of maximizing the likelihood of an insurance payout if there's an event. You minimize the policy costs by answering the insurance questionnaire saying, yes, I do multi-factor. Yes, I have firewalls. Yes, I have antivirus. Yes, 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 all the way down. That minimizes the cost of your policy. But if there's an incident, the insurance company is going to look at what you actually did. And if you failed to do any of what you said you were going to do, there's a real risk that your policy is invalid and you get no payout. So don't say yes, yes, yes. Give an honest answer and make sure that you do and you continue to do as much security as you've told the insurance company you're going to do. That's the right solution for a small shoe factory. For a large automobile factory, it's a different equation. If you go down, if you've got a large business, 4 of your factories that produce, 1,000 vehicles a day, go down for 3 days. That's what, 10, 12,000 vehicles you didn't produce. What does, one of these vehicles cost? It sells for like $40,000 each. We're talking a multi-$100 million hit. You might not be able to buy insurance for that anymore. Is it reasonable? I mean, if you take this in, if you go down, let's say you only have 4 factories, all of your factories go down for 3 days. That's 1% of your year's production that you lost. There's 365 days in the year. Can you afford to lose 1%? Well, yes, you can. That's quite likely an acceptable loss, provided that, again, you have engineering grade protections in your designs to prevent injury to the workers. That might be an acceptable loss, but you're probably still going to suffer a shareholder lawsuit. It's not going to be seen as reasonable. Due care is defined as doing what any reasonable person would do in the circumstances. It's a legally defined term. What is reasonable? It depends on the jury. It depends on the judge. It changes over time. And so what we have to do is ask the question, is it reasonable to suffer a $400 million loss when we could have spent $1 or $2 or $3 million on network engineering and take that loss off the table? And so, the answer to what's reasonable, it depends on return on investment. So for a small shoe factory, you might say, buy insurance. For a large automobile enterprise, you might not be able to buy insurance, and it might not be reasonable to suffer the loss. You might want to do network engineering, not because you have to for public safety, but because it's the reasonable thing to do. For a small water treatment plant, these people have no budget. I mean, I grew up in a town of 10,000 people. There were maybe 8,000 households. Each household spends $1,000 or $1,200 a year on drinking water and sewage. You're talking a $10 million a year budget, most of which goes to pay people in trucks with backhoes to dig holes and fix pipes or lay new pipes. That small utility has no engineers on staff. They have no security people on staff. They're lucky if they have an IT person on staff. Yet, what I see these businesses doing, engineering grade, if you look at, let's say, the drinking water treatment system, there's often no way, there's physically no pipe that leads from the well or the river, that leads from the water source into the water distribution system. The only pipes that lead into the water distribution system go through the treatment system. And so there's not really a risk of sending untreated water into the distribution system. The piping physically prevents that. But a lot of the water treatment systems nowadays are automated in ways that no employee at the water utility understands anymore. This represents a reliability risk. If you lose the ability to treat water, if the water distribution system goes dry, not only do you have a drinking water crisis, you have a sanitation crisis. You cannot flush your toilets anymore. Okay, this is very bad. And what I see a lot of these small utilities doing is they mess up false economies. They have a spreadsheet that says, look, if I enable remote access, it's going to cost me $2,349 a year to enable this remote access system. And I'm going to save $23,652 a year because 17 of my vendors do not have to travel the site. I can save 17 site visits. You do the math and you're coming out $24,000 ahead. It's there in the spreadsheet. Yes, but have you accounted for the $250,000 or $500,000 cybersecurity program, $500,000 a year cybersecurity program that you need to put in to protect the public from a crippled water system? No, that's not in my spreadsheet. I'm sorry. My advice, I mean, this is old school. My advice to small water treatment systems is if you cannot pay to mitigate the risk, you should not be incurring the risk. All of us who live in small towns would rather pay a little bit more for the water and have the water treatment system air gapped so that, hacktivists on the other side of the planet who have it in for us, so that ransomware with nation state grade attack tools cannot come in and impair the water treatment system. If you can't pay for the security, you shouldn't be taking a risk. Controversial. People disagree with this. Oh, air gaps are old. Yes, but look at the consequence. The consequence is unacceptable. The engineering profession has an obligation to protect the public from unacceptable consequences. Power plants are sort of the easy case. The consequence is often there's often safety consequences at power plants. You mess up and you have an ammonia discharge. Why is there ammonia at power plants? It is used to clean the what goes up the smokestacks, so you don't have smog. If a massive ammonia tank breaches, people die. It's very bad, not just for the workers at the site, but for any nearby communities. And so, unacceptable consequences. We need network engineering to protect us against the pervasive threat. A consequence that a lot of us forget about is equipment damage. I'm sorry, if you damage a turbine, that's a 9-month downtime while a new turbine is built from scratch to your specification. There's no worldwide inventory of massive turbines. So, insurance might protect, pay for some of, these turbines, a large turbine is $400 million. Insurance might pay for some of that, but it's not going to protect your population. Again, the engineering community has an obligation to protect public safety and national security. I'm sorry, why is a power plant critical to national security? I'm sorry, large power plants are critical infrastructure. Critical, the definition of critical means critical to the nation, critical to national security. We have an obligation to prevent outages of critical infrastructure. Network engineering is what we use here. I've talked about network engineering. Chapter 8 is about everything else. If we have network engineering in place and we have, as much as practical, reliably prevented attacks from entering the system through the network, I'm sorry, there's still USBs, there's still contractors coming in with laptops. We need to define a design basis threat for that threat actor. Now, I don't believe that it's reasonable for most industry. Now, nuclear generators are an exception, but for most industry, you're not going to see the threat. It's not a credible threat that a nation state is going to go into a small water system and plant, 3 spies 20 years ago in the water system that are, 20 years later going to, turn on and sabotage the system. That's just not a credible threat. The nation state threat, nation state ransomware, is a credible threat across the internet. It's, for most of us, not a credible threat locally. So we have to design we have to set up a design basis threat statement. And here's an example of one that represents what threat we regard as credible in sort of the everything else category, aside from nation state coming across the network, and design our security system to reliably defeat that class of threat, which is often, we want to reliably defeat insiders making mistakes. Okay. An insider making mistakes should not be able to impair national security, should not be able to impair public safety. But, the threat of a deliberate, an insider backed by a nation state taking us on is probably not credible for a small water system. So that's the discussion that happens in Chapter 8. The measures I discuss, I talk about in Chapter 8 are not surprising. Anybody familiar with the NIST framework is familiar with these measures. And the question becomes, how intensely do we provide, or do we apply them? And that's a function of the design basis threat statement. So that's what I had for you. I've run a little overtime. My apologies. We might have to run a bit overtime to take questions. The book is available at the URL on the bottom. Waterfall is giving the book away for free as in celebration of the launch. We're not able to send to all of the world's nations. If you're calling in from Brazil, sorry, you might have to go to Amazon to buy the book. I have tried to drop the price of the Kindle version of the book to the very minimum in any nation that we cannot send books to. So the book should be available to you one way or another. But in most of the world, go to the website there, ask for your copy of the book. We're starting to ship the book. The print runs are done. Thousands of books are in print. We have over 1,000 requests. So we're going to try and answer those requests as quickly as we can. But be patient. It might take another few weeks before you receive the book that you've requested. But the bottom line here is, here's my email. By all means, when you've read the book, send me feedback. I welcome feedback. I don't make up most of this stuff. I learn from people like you I use your feedback. I learn from your feedback and, try to get better the next time. So please do tell me if it's useful. I'll take good, I'll take bad, I'll take ugly. Again, in my first book, the worst feedback I got was, Andrew, I disagree fundamentally with your premise. So I'll take it all. There's only one way to learn. The bottom line, public safety demands engineering grade protection wherever practical. Critical networks where the worst case consequences of compromise are unacceptable. Critical networks have to carry the pervasive threat load reliably until the next opportunity to upgrade to a stronger security system, with a large margin for error. When the consequences of compromise are unacceptable, we have to build a large margin for error into our defenses. Network engineering at criticality boundaries is what we have to do to address the pervasive threat of nation-state ransomware. And the bottom line is, we have to, as an engineering profession, as a cybersecurity profession, we have to exercise due care. We have to do what any reasonable person, what a court, if something comes to court, someone dies or there's a huge loss, if it goes to court, we have to be able to demonstrate the decisions we made were reasonable. They are the same as any reasonable person would have made in our circumstances, had they known what we know at the time we make the decision. And just a word on the side, if it ever comes to court, it helps enormously if we've documented our decision process. The courts do not demand that we are perfect in our decision process, but they do very much appreciate a thoroughly documented process. They give us credit for being thorough, even if in the end we made the wrong mistake or the wrong decision. People do make mistakes. So exercise due care, document the decision process. I hope you find the book useful. Please, give me feedback. That's what I had. Natalia, have we got any questions in the queue?
Yes, Andrew, thank you very much. Great introduction. I can't wait to receive my copy of the book.
It's coming. It's coming. See,
yes.
even Waterfall people don't have the book yet.
I know. Yes. We've got quite a few questions, actually. We'll probably have to go over the top of the hour. I mean, we're almost there. Yes. First question is, do we need to use two-factor authentication when connecting SCADA network to corporate network?
That's a good question. And again, the answer depends on the nature of the industrial network and the worst case compromise. If we're talking, two-factor authentication so that we can remote into a safety instrumented system, I would say no. Don't use two-factor. Don't use remote access at all. We have no business remoting into a safety instrumented system. That's just too dangerous. If we're talking remoting into a small shoe factory, the question is, what does your insurance company demand? Two-factor is a best practice for remoting into SCADA systems when the consequences of compromise are acceptable. Can we remote into SCADA systems where the worst case consequences are unacceptable? Well, I would rather not use two-factor, but it's a hard question because not all threats, not all risks have engineering grade mitigations. So for example, if you can avoid remote access at all, do so. How could you do that? Let's say I need my turbine vendor to come in and help me repair a large turbine. They're the experts. They built the turbine. Put a unidirectional gateway in place and activate remote screen view so that the vendor can log into a website, can see the screen on the turbine vibration system, but the hardware of the gateway says nothing can get through. And so how can the vendor do any kind of support? Well, they're on the phone to someone, the engineer on the inside who's moving the mouse. They can see the mouse move. They can't control it, but they can see it. They can say, no, that's communication diagnostics. Two further down, there's vibration diagnostic. And they work together. And, the vendor thinks they're supervising the site, the engineer on site is not a mouse monkey. The engineer, they're the ones going to be fired if the turbine shakes itself to pieces. So they see the process as supervising the vendor. They're asking questions, they're taking answers, or taking notes. Each of them thinks they're supervising. The remote screen view is a way to get so it's supervised remote access without exposing a network to remote control. If you can do that, do that. When might you use two-factor on a network with unacceptable consequences of compromise? Well, you might need IT to come in and help you from time to time. Your IT people are your experts. They're insiders. You trust them. They've been through your criminal background checks. They've been through your safety training. They're part of the team. In that case, yes, use two-factor, use a firewall, use a jump host, use a VPN, use every piece of software mitigation known to humankind, and insert a device. The one I'm familiar with is called a secure bypass device. It's a device that is copper in, copper out with a physical key. If you turn the key, electromagnets connect the device, connect the copper, and now you have a 1 gigabit connection through the copper into your super hardened remote access system, into your critical network with unacceptable consequences. But there's a physical timer in the device. The device gives the site control over when anyone can access the software two-factor system. The device gives the site control, and the device has a timer in it, typically set for 30, 60, or 90 minutes, a hardware timer. And when the timer expires, the key pops back, the electromagnets separate, and you have nothing can get through the device. There's physically no connection for electrons through the device anymore. So if you must have remote access into your critical network, at least put every kind of software protection on there you can, and put some hardware in the way so that you're not exposed to constant nation state grade attack. You're only exposed an hour every month when you need a GRU to come in to help you. The bottom line is, it is complicated. I've tried to provide a prescriptive answer in the book. There's a lot more context in the book. Have a look at the book, read through it, get sort of the big picture, and then we have to exercise judgment. And we're going to be called upon to answer the question, is it reasonable to expose our safety critical network to remote access an hour a month because we need it? How urgently do we need it? What are we saving? Somebody driving in, we're saving $1,000. Is it worth that for $1,000? But sometimes I'm sorry, that's the only way we can operate it. The substation is 1,000 kilometers away. You have to put someone in a helicopter to get out there. If you want to maintain it at all adequately, you have to use remote access. The question is, do we have to use remote access? Is it reasonable to use remote access? And it depends on the circumstances. And without sort of a strong discussion of costs and benefits specific to the person who asked the question, you can't give it, there's no general answer. But I've meandered on. Hopefully that gives you something.
Thank you, Andrew. Another question we have about major OT cyber attacks in 2023. Can you list some of those?
I have not been tracking it. The one that was sort of in the news was MGM. Wasn't heavy industry. It was, a large, I think it was a casino. People couldn't get into their rooms. That's the one that sticks in my mind. There hasn't been a colonial on the front page. I've seen a couple of incidents that, haven't yet been determined if they were cyber or if they were something else. A data center in Singapore went down. All credit card processing in the nation failed, and it was because of a heat problem on the OT side. But it hasn't been determined, hasn't been said conclusively that was cyber. So anybody attributing cyber to that currently, I think, is speculating. The short answer is there hasn't been a big headline. But the initial numbers, I was talking to Reese McNamee a couple of days ago. He's the one leading the research effort. He says the initial numbers are looking probably to come in somewhere between 75 and 150 this year, but no massive headlines yet.
Thank you. Next question we have, no good copy. Yes, sure, but how do we know for sure that the copy isn't compromised beforehand?
Say that again.
Hold on. No good copy. Yes, sure, but how do we know for sure that the copy isn't compromised beforehand?
No good copy. What does no? Oh, no. Oh, okay.
Yeah.
Sorry, KNOW. I thought it was NO.
Yes. Yeah. Yeah.
Not
No.
a good copy. Yeah. So here's the thing. In my first book, I coined the first 3 laws of cybersecurity. They're in the appendix of the Gold Book. Nothing is secure. Given enough time, money, and talent, anything can be breached. All software has bugs. Some of those bugs are security holes. So in practice, all software can be hacked. Some of those holes are known. Some of them our enemies are using against us because we don't know them yet. Some of them are neither of us know. The third law is all cyber sabotage attacks are information. And any mechanism that allows information to flow, in the worst case, allows attacks to flow. And so if we have malware in the industrial network already, and we've compromised, let's say, the OPC server, and we've falsified some of the data in the OPC server, and we copy that false data to the enterprise, the false data is on the enterprise. That flow of information allows attacks to move from the source to the destination. So, how do we prevent that? Well, this is why we have Chapter 8. Cyber-informed engineering is a coin with 2 sides. We don't choose engineering grade protections or cybersecurity protections. You don't choose one side or the other. It's a whole coin. We need the whole coin. The businesses that I see using engineering grade protection the most intensely also use cybersecurity protection the most intensely. What parts of it? Detect, respond, and recover. We've got to be watching like a hawk our industrial network to make sure that we haven't carried an attack into it if there's network engineering in place, or if there's no network engineering in place, that we haven't allowed an attack through the firewall into the critical network. So yes, there is no, if information is flowing from one source to another, it's always possible to compromise from one source to the other to some degree. To what degree, it depends. Have a look at some of the discussion in chapters 3 and 5. What most people want to prevent, though, is not, what's the worst that happens if we have the wrong data flying out to the business? What's the worst that happens? Well, the business makes wrong business decisions. We schedule maintenance incorrectly. We suffer more mechanical failures in the OT network. We have to spend more money on repairs. These are all business consequences. The reason we do, for example, predictive maintenance is to save money. What's the worst case if information leaks and attacks leak in the other direction? Things blow up, people die. So most of us on the engineering side are worried about preventing the worst case on the industrial network. We also need to think about, not being stupid and losing money on the business side. And again, both reasons are why we use both sides of the coin. We need to detect, I gave the story of the bridge saying, is it reasonable to hope that we can detect the attack in time? Don't get me wrong. We need both sides of the coin. We need detect, respond, and recover. Nobody, deploys an overpressure valve and says, well, that's it, I'm done. Nobody puts their feet on the desk. Again, we need both sides of the coin. We need cybersecurity. Cybersecurity is, the second line of defense to prevent that kind of compromise of the industrial system and prevent that compromise leaking into IT and costing us money. I hope that made sense. I wandered around. Sorry, I'm too excited.
Thank you, Andrew.
I mean, to a degree, this is why I write. I'm not that good actually verbally. This is why I don't debate. This is why I write, because I have my best ideas the morning after and try to write them down. So I hope that made sense.
And another question we have is in regards to water treatment plant. Are you aware of the Oldsmar incident and what happened there?
Yes, indeed. And in fact, we did not count Oldsmar in our threat report because there were no physical consequences. The water was not poisoned. It was an attack. The operator saw the mouse moving. In fact, there are reports after the fact saying it was an insider who made a mistake. It wasn't actually an attack. It doesn't matter. From the point of view of our threat report, there was no physical consequence, so we did not count it. We counted it as a near miss, not as an incident. Yeah, it's an example of the dangers of remote access. You have to manage remote access really aggressively. You have to monitor it really aggressively when the worst case consequences of compromise are unacceptable. So I'm very much aware of Oldsmar. And what happened was an unused, they'd moved to a more secure remote access system, but they had not yet deleted their old TeamViewer, and it came in across TeamViewer, the old unused password. So again, it's a reason that engineering teams who are responsible for networks whose worst case consequences of cyber compromise are unacceptable. When you've got unacceptable consequences, you need to be deeply suspicious of remote access. This is just an example of that. For a small water system, I don't believe there should be any remote access. It's just too dangerous. You can't ask a small water system to burn $500,000 a year on a robust security program. Don't go there. Air gap. Yes, it costs you a little more. Air gap anyway. It's going to cost you less than an incident. It's going to cost you less than the risk to the public. It's reasonable. It's what this is the reasonable thing to do. Okay, I'm done.
Thank you, Andrew. Do you want to take one more question and maybe?
Sure, let's go for it.
Wrapping it up. Okay. What happens when information has to enter an important network, for example, antivirus updates?
So what I document in the Black Book and in Appendix B is, look, we urgently need a test bed. The test bed should at the very least have one of each kind of hardware and software that you have in the industrial network. Ideally, it's a more accurate, a more fleshed out copy of the industrial network. When something like antivirus comes in, it goes into the test bed. And how does it come in? Well, 90% of our customers bring it in manually. They write to a write once CD. They carry it across the room. They put it into a machine that's electrically connected to the OT network, and they insert the antivirus into a test bed, not the OT network. And then they run the antivirus on the test bed to make sure that it's not it's authentic, because the antivirus server will reject a signature file that hasn't been signed correctly, and B, to make sure there's no mistake in the signature file that's going to quarantine half of the industrial network and cripple operations in a critical infrastructure. So yeah, we need a way to get the information in the first place. Manual is best, but there's other alternatives. Have a look at Appendix B. We need to test those signatures to make sure they're not going to cripple our system by accident. And then, we need to move them into the system and roll them out. So yeah, it's not easy. It should not be easy to move information into a network whose worst case consequences are unacceptable, into a critical network. It should never be easy to move information into there. It should always be hard. We have to do it. But if it's easy for us, I'm sorry, it's going to be easy for our enemies as well.
Okay, thank you, Andrew. And once again, congratulations on your new book. I think, well, that's it for today. We'll answer the rest of the questions, as I mentioned, we'll answer it via email.
Absolutely.
Once again, on behalf of Waterfall, thank you for joining us today, and we'll see you next time.
Thank you, Natalia. Thank you for everyone joining. And, do take me up on the offer. Read the book, send me feedback. I can only learn from you folks. Again, I don't make most of this stuff up. I learn from practitioners like yourself as to what works for you, what doesn't. And, that's how we get better over time. Thank you so much.
Thank you, Andrew. Bye, everyone.